So let me start with the few questions that we have asked in the last class. Is there any other norm other than modulus on R? Other than modulus. Okay, so the answer to that question is, if you have thought, any of you have answer? Of course, many of you said yes. So what do you mean by other norm? Means if there is any other, at least for some vector, norm of modulus and norm of the other thing which you are saying, it should be different value. It should, at least at one point, it should differ value. Then only it is different now. Okay. So as somebody said, who said that? Anish?
Yes, sir.
Okay. So it you just check that. So if I multiply this 2 times, so the function is 2 times mod x. What is that? What does it mean? Again, make it clear. So my new norm is a function from R to R. Here, this is a vector space, and this is the usual place where it is landing. It defined by norm of any x is 2 times modulus of x. This is something. And check that it is a norm, and then there is nothing special about this too. In fact, one can replace this by any scalar. Of course, we have to take the positive scalar. You cannot take 0. That will be a problem. So you have to take a positive scalar. So you can check that it is a norm. And what more important I want to ask is that this is an exercise for you to take it back. That is, prove that every norm will be like this only. So if at all there is a norm on R, if there is a norm on R, it will be always some scalar multiple times mod x. So that you can check. Okay. So that's an exercise. So all norms are like this only. Okay. And I hope you would have checked what are the other exercises that I left out. What are the elements in Rn where the norm 1 and norm infinity are same. So we'll come back to that maybe later. Okay, so now we'll get into what we are supposed to. Let us go further. So far we have looked at examples like where the vector spaces R are Rn's, and then appropriately 2 different norms we have defined. And it has suggested that on a single vector space you can have 2 different norms. Now we'll go ahead. This was the plan in the last class also, to go for a general setup. So in that regard, our aim is to look something like R infinity, this whatever it means. Okay. So infinite copies of R is what we are trying. So in that context, I will first want to check the following: that I collect all functions defined on some set x. Okay, so x is some. We want to be more precise, so let me call it as it's a non-empty set. Now I want to consider the following, that is all functions which are going from x to R. These are all functions. So I want to call with some name. Let me call it as these are all functions where it is starting at x and ending at R. So the first question that I want to ask is this a vector space? Okay. So is it a vector space? Of course, to say that it is a vector space, one has to say that what is the addition and scalar multiple. What is the addition? So if you give me a function f from the space, f and g from this fxr, then I define f plus g. It's a new function, but any function I know by defining what is its value at any point in x. So it is defined as f of x plus g of x. Similarly, what is the new function alpha f for a scalar is defined as alpha times f of x. Okay, good. So this one is what is called point evaluations. So or what you call point-wise addition and point-wise scalar multiple. Or if you want, you can consider element-wise. Now, with respect to this, now I want you to quickly check or recall. Have you studied somewhere? Then tell me that is it a vector space? And if you know that it is a vector space, then say yes. Okay, so the way that you are answering, it appears to be that not many of you are unable to recollect or you don't want to react. Okay. Good. Okay. I'm clearing it off. So this is a vector space on which now this is a vector space. So this is like our basic vector space. Now on this vector space, we want to define a norm. So what is that? What is our aim? I want to define a norm from this fxr. Remember in our abstract definition, this is now our capital X. To R. How it should be defined, it is norm of any element here is of the function. So I should define what is this. By the way, I hope you know this notation also. So this says that this notation says that wherever you have put the left hand side is the notation and right hand side is defined by. Okay, so this is the notation and this is definite. Okay, so sometimes we may put the dots on the other side, so point of space. Anyway, so the norm of f is the notation which is defined by. That's what this dot equal. Okay. So any suggestion? How many of you know what kind of norms that we can define? So there is a there is a
We can
natural. Who is that? Who is it answering?
So me, Data.
That okay.
We can define mod of integral of f of x dx, but it sometimes it attains value in extended real line.
Yeah, correct. So there are options. So Datta is saying. So let me call this as. This is what you want to say?
Yes,
F
sir.
of x dx. Okay. So this is by Datta. Any other suggestions? No, there is somebody with the name ES17 BTech. If you change into your name, it will be easy for me to. So as soon as you get in, you please change your name. You can do that just on the participants, click and right click, and you will be able to change your name. Yeah, any other suggestion other than this?
Say modulus of fx.
Okay, so you are saying that modulus of f of x. Okay, what is the x? This is by Piyush. Yeah, Piyush,
Okay, okay. I think that will not a no.
this is not a norm. Okay, any other answers?
So maybe we can have supremum of mod of x varying as in
Minimum
capital
of
X,
model.
but we have to take actually we can have
This is
infinity. So
this is
it's
Atanu.
will not,
Okay.
it will not be actually.
Yeah. Supremum or all x. Okay. Okay. So you are saying a little more also. Yeah. Anything more? Any other suggestions? Maybe I'll ask particularly. Let's say Vijay. Vijay.
Yes, sir.
Yeah.
Sir, I think
Saj.
integration of f of x dx is correct. Tatta.
What data said, that's what you are thinking. Okay.
Then
So, but Vijay, Datta suggested this, but will this integration be always non-negative?
Sir.
We want that norm to be non-negative, right?
Yes.
So what change you can do?
Integration of mod f of x dx.
Maybe that's also a good idea. So what Vijay is suggesting is that maybe this we can do. We can put mod of x. So at least I am sure of I'm integrating a non-negative function, so the integration also may be non-negative. Thank you, Vijay. Yeah, Piyush himself want to drop this. So any other suggestions? Sai Nikhil.
No, sir.
What is no? Sai Nikhil. No for what? Oh, you have some network issue? It's okay. So there are,
Yes.
yeah. So yes for the network issue is proper. Okay, so there are options. So how many of you think, so I'll call this as 1, 2 and 3. I'm calling with the name. So just send a chat message that which of you think is a norm. One with the mod. Data is also accepting that. Take the modulus of integration. Piju says none. Sugita says none. Mohan says the third one. Bhumi none. Okay. Tanamana none. Jayant Rangi says 1, 1, 1. Anish says none. Jain says 1 and 3. Ritesh says 1. Sujana says 1 and 3. 3 and 1 with mod. Mod of integral f. Okay. Prachi says that. Good. So most of you are giving some answers 100. What I would suggest is that what you are thinking and the answers all are right. Each of them has its own merit and demerit. The reason is the following: that you are just thinking ahead. Maybe it is true, but if you step by step, if you verify, you will be able to see why it happens and why it doesn't happen. For example, we have to make sure let us discuss about the first definition. Suppose if we are discussing about taking the first definition, which was given by Datta and then corrected by Vijay for the non-negativity, can you see that if this integration, I want to define it for all functions which are going from x to r. But you may be knowing this already familiar that do we know, are we sure that all functions we can integrate? Yes or no? Do we know that we can integrate all functions? This is the first thing that you will learn, that there are something which you can integrate and something you cannot integrate. Good. So if at all I want to define the first one, I should make sure first of all this is integration. So possible way is that the straight answer is no, it is not a norm because I cannot integrate all function. But there is always an alternate. So what is the alternate? Maybe for this, I don't want to consider the full functions, maybe integrable functions. Okay. So I may consider some other set called E, which is subset of this, or let me write, let's say R. This is a different R. Okay. Which let us call, I consider only the Riemann integrable functions, which are inside this function. Then it may become integrable. That's one possibility, maybe. Okay. Look at the second condition, second definition. Most of you said no. The answer is clear because what creates the problem? This is anyway non-negative number. There is no problem in it. But if I say that the function definiteness creates a problem. If mod f of x, norm f is 0, that means I can conclude f of x is 0 only at that point x. Other points we don't know about the function. But what we need to conclude is the function itself is 0. What is the meaning of function itself is 0? An element here is 0 means the function 0 means f of that function value at any point is actually 0. So here the 0 function is, so the real reason here is if 0 is in f, xr, it's actually this function defined by 0 of x is defined as 0. Okay. This is for all x in x. So this is what we call it as the 0 function. But that we may not get it from this. That's why you are dropping the second. Most of you have not chosen the second one. Third one, and now after discussing this, can you see the third one also has a similar problem? Is it true that if I take any function, can I always find out a supremum? As of now, x is any set. So for any x, it may have a problem, right? For example, very specifically, suppose if I consider f r r. So for this, suppose if I consider f, I take x to be also r. Then I know that the function f of x equal to x. Okay, this function belongs to the set. But what is the supremum? With modulus, it becomes infinite. But I want this to be a real number. No? Norm has to be a real number. And so this creates a problem. So this is creating a problem, and hence we can say that no, the 3 is not defining a norm on this set fxr. But we don't need to stop at that stage. We can go a little further and say that I consider only those functions for which this supremum exists. Okay. So now how many of you can, so what conditions on x? So the question is the following. So what conditions on x will make the third definition a finite number, real number. Is the question clear? Just think that what are the conditions I can put on x so that I can actually define the third condition. One can ask such question. there is something called Sujana has sent something called absolute convergent. But right now, this is just about a function. Some condition on functions only you can put. There is no convergent as such. You want to say, yeah, yeah. What do you want to say, Sujana? Can you see that? For that function, you want to have supremum should be there. So,
Hello, sir. Sorry for
yeah,
disturbance. Sorry,
yeah,
sir.
yeah.
Sorry, but Vishal is trying to join, but he's not allow. You are
Okay.
not allowing you. He has some network issue, but he's
No, no,
still
no, no,
trying.
no. You can tell. You can ask your friends to send a message to you and tell me. Just now I added.
Okay, 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 okay.
Okay. So yeah, so good. There are some answers. I'm just going to tell, and you have to say yes or no about these conditions. Okay. Condition, first condition. You can see that there in the chat. X is finite. If I say that my set X, this X, if it is finite, then I can define the condition 3. You all accept? Because what happens in that case, the supremum is, suppose that set is containing only finite, that means x1, x2, x3 or xn. Then supremum of this is nothing but finding the supremum of f of x1, mod of f(x1), f of x2, f of x3 and f of x1. Those finite numbers supremum you have to take, and hence it becomes just maximum. Right? So finite set is one answer. So if x is finite, yes, I can do that. That's good. There are some people who have answered that you consider only the functions which are bounded. That means I am not considering the full f. So maybe I'll call it as B, which is subset of this XR. That means bounded functions from X to R. By bounded function, you might have known already, there exists M, capital M, such that for all X in X, F, modulus of F of X is less than or equal to M. And hence the supremum also has to be less than or equal to M. By the way, supremum means LUB. So I'll prefer to use LUB. So is the second one is fine. Suppose if I consider only the bounded functions, I can still define the third definition. Maybe I can still check whether it is or not. At least this becomes a finite number. Any more answers? Right. What if I consider only the continuous functions? How many of you think it is true? I'm clearing it off. The question is that suppose if I consider the function to be only continuous, then the third definition defines a finite number. Good. Half of you are saying no. Good. There is a evident example, whatever we did, f of x equal to x. It's such a nice continuous function, but again, this third definition doesn't make sense. Okay. But there are some other answers. Somebody said that you can consider continuous function, but you have to put two conditions, some condition on the function as well as condition on the set called compact sets. Good. Now what we want to do is that once you observe all these facts, now we want to quickly go through the following. So all discussion is leading to the following. That answer to this is that none of these 1, 2, 3 is actually defining a norm on FXR. But if I consider BXR, what is this? The set of all functions from X to R such that F is bounded. So if I consider this, then I can possibly consider norm of f is defined as supremum of mod f of x such that x is from 1. Okay. So by notation wise, we will write both this. Both are same. Okay. We may also write sometimes LUB. Or sometimes this may go inside this set. All these are equivalent. Sir, in case 1, there is some question. Which is considered. How can we say it as shown finite value? Okay, so the Prachi's question is the following. Suppose if I say that x is finite and I consider 1 by x as the function, and then it takes at 0 it takes value like infinite. Is that what is your question, Prachi? Prachi? Prachi, you have to speak. Yeah.
Yes, sir.
Yeah.
Sir, I quoted like it is not defined on 0, so we can't consider that function.
Now what is the set you are considering?
The function is 1 by x, and I can consider the set to be 0, 1, 2, the finite set.
Okay, 0, 1 minute. Answer is 0, 1, 2. Just 3 points, let's say. Okay, so what is the
Yes,
function?
sir.
What is f of x?
1 by x.
Is the
As
function
it is not
defined on this
defined on
set?
0, so we won't consider it. Yeah,
Yeah,
exactly. It's not defined. So.
so you have not
Yeah,
given the
yeah.
function. Yeah. Okay.
Okay.
So you have not given the function. If you give the function on finite sets, it has to take finite value and then it will work out. So 1 by
Okay, sir.
x, yeah, 1 by x is not a function defined on R. Because at 0, you have to tell what is the value. At every point, the function has to be defined. Otherwise, it's no more a function. Okay. So hence you get this as the norm, and now we want to check whether it's actually a norm. But before that, remember, whenever we just do some what to say that change of base, change of the underlying set, we have to be little careful, because means we have moved from fxr, which I know it is a vector space, to some other set which is bxr. It is subset of fxr, of course. But we have to make sure that this is also a vector space, because I can define norm only on a vector space. So let's quickly check, is it a vector space? Is bxr a vector space? If you have not done, then please check. If f is bounded and g is bounded, then f plus g is bounded. If f is bounded, if you multiply with any scalar, that function is also bounded. These things you have to make sure. Okay. So first, let's say bxr is vector space. Okay. So let's go through the. Okay, this is a kind of 0. You are checking the vector space structure. Next, what about this norm? Is it? I'm clearing it. Can you check it is non-negative? I want you to be a little faster now. Say yes or no. Good. So this is fine. So it is non-negative. Definiteness? Good. But just don't blindly believe. I would expect you to go through the proof at least once. So if I give you the supremum of something, supremum of a set is 0, then you want to say that each element inside the set is 0. In fact, here it is supremum of non-negative numbers is 0. Then you have to say that each number is 0. So you have to use the LEB property, and maybe you need to use the fact that this mod f of x is bigger than or equal to 0. So you will get f of x is less than or equal to 0. And another side you will get mod f of x is bigger than or equal to 0, and hence by sandwiching you get f of x has to be equal to 0. If mod f of x is 0, then you have to prove that f of x is 0. So that's fine. So you get definiteness also. And for 0 function, the supremum is 0. The other way also we get it. What about quickly 2? Scalar multiple. Good. Triangle inequality. So what we need to show is supremum of f plus g of x. This is over x. This is less than or equal to supremum of this is what we need to show. So I give you just a picture and see that whether it makes sense. So this is my set x. I have this function. This is my f, and then this could be my g. So what will be what is that we are trying to find out geometrically? Also you try to understand. If this is f, first of all we are finding the mod f. So that means, I hope you know this fact. So mod f, if I consider the function which is on the positive side will remain as positive, but only the negative side it will change. So it becomes, so it is the same f, but the negative part it becomes positive. So the yellow function is the mod f function. And similarly, what is mod g? So on the positive side it will remain as positive, but on the negative side it will be modulus, so it will be flipped. So this will be the function. Okay. So what will be the maximum of g? It looks like this is maybe the maximum. This is the one which corresponds to this value. And mod f is this. This corresponds to mod f. But what corresponds to f plus g's maximum? You have to add these two functions. So you may get some other new function. Okay. At each point you need to add them. I don't know what kind of function you get. Okay, you can think of. But that maximum, wherever it happens, it may not do anything with g and f. Okay. But what we are saying is that line will be less than or equal to adding these two numbers. So is the geometric picture clear? Just take a minute and then okay. So if you are not getting it, please make sure that this is crucial, that we will be using this kind of ideas in certain proofs now and then. Okay, so make sure that you are understanding what I'm speaking. Okay. It's not difficult, this you are aware of. Maybe if I want to make things much easier, suppose on 0 1, if I consider the function this as my one function and this as another function. Okay, so even it's even more easier if you could follow this. Let's say I am taking only between -1 and +1 and this value is 0. So this function is x and this function is -x. And can you see that what will be this? This is f and this is g. Can you see that f plus g is 0? Yeah. So f plus g's maximum is actually just 0. But maximum of f, that means supremum of f, or the LUB of f inside the interval -1 to 1 is 1. And for g also it is 1. But if I take the sum, it can become just 0. Okay, so the supremum is some kind of height, peak, where it is getting its peak. Okay, so the peak of f plus g need not be same as the peak of f plus peak of g. It could be much lower. Maybe it again emphasize that what individually we could kind of achieve will be more kind of information. Right. And once we verified this, so this is just a geometric verification, but one has to actually prove. And here comes the fact quickly. Now, what we have done in the case of Rn, okay, all that we do is the following. I take one element on the left hand side and I will show that that is less than or equal to this. So how do I do that? It is, I consider f plus g of x modulus. I know that by definition it is mod f of x plus g of x. And here I use the triangle inequality for the real numbers now. And I use the fact, remember this I will say again, I want you to go through quickly and very clearly. What is the connection between any element of a set and its supremum? That is the least upper bound. So least upper bound is also an upper bound. Okay, that means this f of x has to be less than or equal to upper bound of the set containing all f of x's, and hence it will be less than or equal to norm. Or if you want, I can write this. This is the one. Maybe I'll write this again. So this is less than or equal to taking LUB of all such things. Similarly, this is LUB of such things. And that turns out to be nothing but norm. And this is norm G. So what we have proved is, say, remember this inequality now we have proved. That is mod of f plus g of x is less than or equal to this. This is what we have proved if I put all the inequalities. Remember, I said yesterday to say that a is less than or equal to b, we are proving a is less than or equal to b, b is less than or equal to c, and c is less than or equal to d. So this is what we have proved, and this is true for any x because the right hand side is not changing. Okay. So now again use the fact. So for all x in x, for this kind of elements, if I consider, for each element in that set, this number, it's a fixed number, that's an upper bound. But if I take the supremum, that's equivalent to, by definition, it is the least upper bound. So among the upper bounds, it is least. So the connection between a least upper bound and an upper bound is always less than or equal to, and hence we get norm of f plus g is less than or equal to norm f plus g. So it might look like unnecessarily re-emphasizing, but remember this will be using number of times. So is this part clear up to this? So we have actually verified the triangle inequality. So geometrically also we looked at. So what we get is that if I consider set of all bounded functions from x to r with this norm, okay. Again, we are taking the maximum or supremum, so we can fix the notation. This is called infinite norm. Or subnorm. Subnorm is called, it is denoted by this infinity. So this is a nonlinear space. So fxr with this norm is not a nonlinear space because we are unable to define this as a function, but bxr we could do this. And again, another thing, at least for the first few days, you can check that whenever you are coming across a norm on triangle inequality, ask the following question. When you will have equality in the triangle inequality, is there any example? Think of one example. And similarly, think of an example for strict inequality. For example, here we have seen strict inequality example, this one. So this is an example of strict inequality. Okay. So once we have this, now we can define plenty of other things. So the third one, we somehow could succeed in some sense to define a norm on BXR. Now quickly let me do this and then we can go for can break out. Suppose if I consider CXR, what it is defined as set of all functions from x to r such that f is continuous. Okay. So it is not just some just bounded functions. It is continuous functions. Okay. So always think of ask the question that is there an element in BXR which is not in CXR, or is there any subset connection? That's an exercise that you can think. And if I consider the continuous function, can I define the same norm again? That one can ask the question. Again, we have seen example that even when x is the case, x equal to r, f of x equal to x itself is not here. It's continuous, but I'm unable to define the norm. So it's better to consider continuous and bounded. So I will consider CBXR. It's a notation. So these are all functions from x to r such that f is continuous and f is bounded. Now what is this direct connection between CBXR and BXR? If you could see immediately, it is CBXR all functions are bounded. So it is subset of BXR. And hence the question is, can we define from here? How many of you think yes, we can define? Yes or no? Good. So you can define such a norm on continuous and bounded function. But if you have done metric space and topology, I don't need to assume boundedness. By assuming something on x, I can get boundedness. For example, if I assume x to be finite, I will get boundedness free. And if I assume x to be compact, again I get boundedness free because continuous function on a compact set has its maximum and minimum. So it will be bounded function. So specifically if I take x is so if x is finite, we can drop boundedness because it automatically becomes bounded. And if x is compact, Then also, of course, we can drop the finiteness. Just keeping the finiteness is actually enough. I'll give you a few more exercises for you to think. Okay. So the question that we can ask is that, so if x is a finite set, so I'll call it as something like, say, x1, x2, xn. Think of what are these bxr, fxr, and cxr, and cbxr, many spaces that we have defined. That's one question. And also check what happens when x is natural numbers. Can any of you answer what happens to, let's say, fxr? Very specific. So what are all the functions from n to r are called?
Sequence.
Uh,
Real sequence.
no, unless I ask, please don't answer. Let others also think. So verify that this gives you sequence. Okay. And now you can ask the question that what happens when x is replaced in all these spaces. That is, what are all the spaces that we defined? In all the cases, look at what happens to this space and bxr, which we know it is sub, and then cxr and cbxr. And here also there is a subset. This is subset, okay. But directly there is no connection between cxr and bxr unless I put some condition on x. You can think that. So what are all these functions? Make little more familiar, and what it means to say that the function is bounded. If it is going from natural numbers, one can ask such question. And another question that I want to ask: suppose I have a nonlinear space, okay, and say y is subset of x, okay, a subspace. Is there any easy way to define a norm on y? If you say yes, if you think so, then say yes. Is there any? So on a big space, I have a norm. That means I know how to. So norm, if you are still taking time to what it is, think of it as a length. So I know the length of, I know the height of every person in the institute. That's a bigger set. Do I know, can I easily define a height of a person in a class? If I know the height of everybody in the institute, do I know the height of every person in a class? It's a smaller set. No? So there's a natural way that we can define the norm on this y, right? So on a bigger space, if you have a norm, there's an easy way to check, easy way to define a norm on a smaller set if it is a subspace. But the question is not that much alone. The question is that suppose if I know this is a norm on a bigger set, and if I want to check it is actually a norm on a smaller set, what are the properties I need to check it again? Okay. Do I again need to check it is non-negative? No need, because it comes from the bigger set. Do I again need to check the triangle inequality? No, it is true for in a bigger set. So do I need to again check homogeneous? And do I need to check the definiteness? So go through this and ask the question that if I have a norm on a bigger set, will I be able to always define a new norm on a smaller set, smaller subspace? And is there anything really I need to check, or it automatically becomes a norm? That's the question you can ask. Okay, so we'll stop with that, and now we are done.